picture this for a second. You're sitting in your room at night, you flip off the lights, and darkness completely fills the space. Now, you might think you can't see anything, but honestly, your eyes eventually adjust, right? You catch that faint street lamp glow from outside, or maybe the fuzzy outline of your walls. That's not real darkness. I want you to imagine a darkness so absolute that it literally doesn't reflect light, doesn't emit it, doesn't absorb it, and doesn't interact with the electromagnetic spectrum at all. To our eyes, and even to our most insanely powerful optical telescopes, it's completely invisible. But here is the massive, almost unbelievable twist we're exploring in today's explainer. This invisible, ghost-like stuff actually makes up almost everything in our universe. Look around you right now. The chair you're sitting on, the screen you're watching this on, the trees outside, the sun shining in the sky, all of that is made of atoms. Protons, neutrons, electrons. You know, the normal stuff. But here is the shocking truth about our cosmic recipe. If the entire universe were a pizza, the atoms making up the stars, the planets, and, well, us, would be nothing more than a tiny little sprinkle of cheese on top. Literally everything humanity has ever seen, touched, or known makes up a mere 5% of reality. The rest of that pizza? It's something entirely different, and frankly, something we fundamentally don't understand yet. So let's break this down. If everything we interact with is just a measly 5% of the universe, what on earth is the rest of it? Well, scientists have figured out that this remaining 95% is basically a massive unsolved mystery divided into two huge chunks. We've got 27%, which is dark matter, and a whopping 68%, which is dark energy. Together, they form the invisible skeleton of the entire cosmos. So today, we're going to go on a journey to uncover exactly how we know this unseen world actually exists and what it ultimately means for the future of, well, everything. Let's kick things off with Section 1. Discovering the invisible glue. To really get into this cosmic detective story, we have to rewind and walk through about 70 years of astrophysics. We need to see how scientists slowly realized we were missing the vast majority of the universe's mass. This definitely wasn't some overnight eureka moment. It actually started way back in the early 1930s when astronomers realized spinning galaxy clusters should just fly apart based on the visible mass they could measure. Then, in the 1970s, the focus shifted to individual spiral galaxies acting just as bizarrely. Fast forward to the late 90s and 2006, and our observations expanded to cosmic expansion and epic galactic collisions, giving us direct, undeniable evidence that our universe is totally dominated by the invisible. Let's start right here with the brilliant Swiss-born astronomer Fritz Zwicky, back in 1933. He was studying this huge group of galaxies called the Coma Cluster, and he noticed a pretty glaring anomaly. The galaxies in this cluster were just moving way too fast. Based on all the laws of gravity from the ordinary glowing matter they could see, these stars should have been launched out into deep space. Think of it like kids getting flung off a merry-go-round that's spinning totally out of control. To wrap your head around this, imagine throwing a bunch of rapidly spinning tennis balls into a bucket of water. If you only look at the tennis balls, the system looks completely unstable, right? They should just bounce away. But the hidden water in the bucket, that provides the friction and the glue holding everything together. Zwicky suggested there was an unseen mass providing that gravitational glue for the galaxies, and he called it dunkle Materie, German for dark matter. Now, for a really long time, Zwicky's idea was just seen as this fringe, kind of weird concept. People basically ignored it. But that all changed in the 1970s, thanks to the incredible American astronomer Vera Rubin. She was observing the outer edges of spiral galaxies and stumbled right into the exact same missing matter problem. The stars out on the very fringes of these spirals were whipping around so fast that, without some massive amount of unseen glue holding them in place, they should have been ejected into intergalactic space. Rubin's data was just so meticulous and undeniable that the scientific community finally had to face facts. Dark matter wasn't just some quirk of one single cluster, it was literally everywhere. Which brings us nicely to Section 2, seeing the unseen evidence. Okay, so here's the huge million-dollar question. If dark matter isn't stars, it isn't dust, it isn't black holes, and it doesn't absorb, reflect, or emit any light on the electromagnetic spectrum, how do we actually find it? How do we see the unseen? The answer is something called gravitational lensing. Because dark matter has mass, it definitely has gravity. And that immense, localized mass can literally bend the fabric of space-time itself. So when light from really distant background galaxies travel toward us and passes by a massive invisible cloud of dark matter, that light gets bent, creating these wildly warped and magnified images. It's so cool. That's how we track it. Think about the wind. You can't see the wind, but you absolutely know it's there because you see the leaves blowing in the trees. Or Wi-Fi, right? You can't see it, but your phone catches the signal. We track dark matter purely by the gravitational pull it exerts on the stuff we can actually see. And what's really amazing is how this leads us to the best, most direct fingerprint we've ever found of this cosmic ghost, the bullet cluster. Observed back in 2006, this thing is essentially a ridiculously epic cosmic car crash. It happened when two massive galaxy clusters smashed into each other about 3.8 billion light-years away from Earth. During this unbelievably violent collision, our telescopes were actually able to map out what happened. Using NASA's Chandra X-ray Observatory, astronomers saw the hot gas of the normal matter, which is the pink stuff, crashing together, interacting, and really slowing down. But using that gravitational lensing we just talked about, they also mapped the dark matter, which is highlighted in blue. And look at this. The blue dark matter totally separated from the pink normal matter. It passed right through the crash site without slowing down at all. It's our most direct visual proof that dark matter exists entirely independently of normal matter. Right. So we know it's out there, but what is it actually like? Well, since dark matter has mass, it has to have a temperature. So scientists fired up the supercomputers and ran simulations modeling our universe with two different scenarios: hot, fast-moving dark matter, or cold, slow-moving dark matter. The results were crystal clear. If dark matter were hot and zooming around really fast, the complex cosmic structures we observe today wouldn't be able to stick together at all. They'd just fall apart. The simulations absolutely prove that this invisible glue must be cold and slow-moving to allow galaxies to form and clump together exactly the way we see them in reality. Moving on to Section 3, profiling the prime suspects. Now that we've got a solid profile of our culprit, invisible, heavy, cold, and sluggish, physicists have gone into full detective mode. All over the world, they've built these massive, ultra-sensitive detectors, deep underground in abandoned gold mines, buried under the ice in Antarctica, and inside giant particle accelerators. Honestly, it's exactly like setting up mousetraps in a house where you absolutely know mice are living, but you've literally never seen one. So who's on our suspect board? Let's rapid fire through the leading candidates. First up, WIMPs, or weakly interacting massive particles. These are heavy, slow, and slip right through normal matter like it's nothing. Scientists are hunting for them using space telescopes, hoping to catch a flash of gamma rays that happens when two WIMPs randomly collide and annihilate each other. Suspect number 2, axions. These are hypothetical, super low-mass particles that were originally dreamed up to solve a complex math puzzle in quantum physics. And finally, primordial black holes. The legendary Stephen Hawking proposed that these ancient microscopic black holes, some with the mass of just a paperclip, formed right after the Big Bang, and basically make up the dark matter we see today. We're actively scanning the skies for their evaporation signatures to see if he was right. Let's shift gears to an even wilder concept in Section 4, the dark energy twist.
Seriously, if you thought dark matter was a mindbender, wait until we talk about an even bigger plot twist that scientists stumbled upon in the late 1990s. And it's super important we clearly separate these two because people mix them up all the time. Dark matter, that 27% of the universe, is the invisible glue pulling galaxies together using gravity. But dark energy? Dark energy is entirely different. Back in the late 90s, astronomers were measuring light from these incredibly distant exploding supernovae. They fully expected to find that the universe's expansion was slowing down, right? Because gravity should be pulling everything back inward. But instead, they found the exact opposite. It was speeding up. Dark energy, which makes up a terrifying 68% of the universe, is basically an anti-gravity force woven into the very fabric of space itself, actively pushing the universe apart faster and faster. Imagine tossing a baseball straight up into the air. Gravity should slow it down until it falls back. But in a universe dominated by dark energy, instead of slowing down, that baseball just accelerates and flies faster and faster away from you into the sky. It's completely counterintuitive.
To really grasp the sheer, staggering scale of the 95% we can't see, just think about these analogies. Imagine standing on a beach watching the surface waves roll in. Those waves, that's our visible 5%. But the vast, dark, miles-deep ocean beneath them, that remains totally unseen. Or think of an iceberg. The stars and galaxies are just the tiny white tips sticking above the water, while the overwhelming majority of the mass lies hidden in the dark below. Or even something relatable like the economy. Imagine thinking you understand the entire global financial system just by looking at the crumpled pocket cash in your wallet, while completely ignoring the massive, invisible digital transfers and hidden assets moving trillions around the globe. That's where we're at. Dark matter and dark energy are the vast hidden reality of our cosmos. And that brings us to our final part, Section 5, the fate of the universe. So you might be wondering, why should I care about something I can't even see? Well, because understanding this invisible 95% isn't just some abstract academic exercise. It is literally about the ultimate survival of our reality. See, right now, dark matter and dark energy are locked in an epic cosmic tug of war. The gravity of dark matter is pulling inward, and the anti-gravity of dark energy is pushing outward. And whoever wins this war determines the fate of everything. If dark energy's push keeps winning, which seems likely right now, galaxies drift so far apart that the night sky goes black, stars burn out, and we end up in step 1, a big freeze. Just a cold, dark, endless void. But if dark matter's gravity somehow pulls an upset and dominates, we get step 2, a big crunch, where the universe forcefully collapses back in on itself into a dense singularity. Or, and this is the terrifying one, if some crazy new physics we don't understand yet takes the wheel, we face step 3, a big rip. That's where dark energy accelerates so violently that it literally tears apart galaxies, then stars, then planets, then atoms, and eventually the fabric of space-time itself. I want to leave you with this kind of humbling gut punch. Humanity is pretty amazing, right? We've built incredible space telescopes, giant particle accelerators, spacecraft that have left the solar system, and advanced AI. And yet, 95% of our own reality remains a total, absolute mystery to us. It really makes you ask a profound question. Are we just a bunch of ants crawling on the screen of an iPhone? We can feel the smooth glass, we can see the glowing colors, but we are completely blind to the incredibly complex circuitry humming away just beneath our feet. We are quite literally living inside a cosmic ghost story, shaped by massive invisible entities we simply cannot see. It turns out, the universe we can't see is actually vastly more real than the more we can. So what do you think we're going to find when we finally crack the glass and look inside? Thanks for exploring this with us.